All right, in this explainer, we are diving deep inside the digital mind. We're going to unpack the fundamental architecture, the very blueprint that powers pretty much all of modern artificial intelligence. So let's start with something that feels like modern magic, right? You point your phone's camera at a sign in a language you can't read, and poof, the translation just appears on your screen. That's not just a clever trick, it's the result of a very specific and honestly brilliant architecture. And the secret behind it? Well, it's an architecture that's inspired by the most powerful computer we know of, the one sitting right inside your skull. It's a whole network of simple digital switches, or neurons, all working together to make sense of the world. And believe me, understanding how they're arranged is the key to, well, everything. Okay, so let's peel back the layers of this digital brain and start with its most basic, most fundamental building block, the single artificial neuron. Meet the perceptron. This thing was first dreamed of way back in 1957 by a guy named Frank Rosenblatt, and it's basically the granddaddy of all modern AI. Think of it like a tiny decision maker. It takes in a few pieces of information, weighs how important each piece is, and then just spits out a simple yes or no. That's it. So what's really cool is how we can turn a decision into simple math. Let's say you're deciding whether to go surfing. The neuron gets inputs. Are the waves good? Yep, that's a 1. Is the lineup empty? Nope, it's crowded, so that's a 0. Are there sharks? No, which is good, so that gets a 1. Then we multiply each of those by their weight, how much you care about that factor. The math is easy. 1 times 5 plus 0 times 2 plus 1 times 4. That equals 9. And since 9 is way higher than your get off the couch threshold of, say, 3, the output is yes, time to go surfing. But here's the thing. For all its elegance, this simple neuron has a huge critical weakness. There's a puzzle so simple it's almost insulting, and yet it completely stumped the entire field of AI for more than a decade. Okay, so look at this. A single neuron can solve any problem where you can separate the yes answers from the no answers with just one straight line. Easy. But now look at the problem on the right, the famous XOR puzzle. The correct answers are in opposite corners. There is no way, literally no way, you can draw one single straight line to group them together. No matter where you draw it, you fail. A single neuron is just mathematically blind to this kind of pattern. And this wasn't just a small bug, some minor issue. In 1969, 2 AI pioneers, Minsky and Papert, published a book that mathematically proved this limitation. And the fallout was so devastating, it actually triggered what we now call the first AI winter. All the funding dried up, research grants disappeared, and progress in the field just about froze solid. So how did AI ever get out of that cold? Well, the solution wasn't some new, better, smarter neuron. No, the solution was all about architecture. It was about arranging these simple neurons in a much, much more clever way. The big breakthrough came when researchers realized, what if we stack layers of these neurons on top of each other between the input and the final output? They created what we call hidden layers. And these layers, they work together to transform the data in stages. This architecture, with its depth, is exactly where the term deep learning comes from. And this, right here, this is the core of the breakthrough. With these hidden layers, the network is no longer stuck drawing straight lines. It suddenly gets the ability to bend and warp its decision boundary, drawing these complex, squiggly shapes to solve tough problems like XR. It's like we traded in a rigid wooden ruler for a flexible one that can trace any pattern you can imagine. But, having the right architecture is just the start. A blueprint doesn't build itself. So how does this multi-layered network actually learn how to draw those complex shapes in the right way? It learns just like we do, through trial and error. A whole lot of it. First, it makes a guess, passing the data forward through all its layers. Then it checks its answer against the right one and calculates an error score. Basically, it figures out how wrong it was. And finally, and this is the real magic, it sends that error score backward through the entire network. This process, called backpropagation, tells every single neuron how much it contributed to the mistake and how to adjust itself just a tiny bit to do better next time. And it does this millions, even billions of times. Now, it's really important to know, this isn't just random tweaking. The network uses this incredibly powerful algorithm called gradient descent. I want you to imagine a giant hilly landscape where every spot represents a possible setting for the network's weights. The lowest valley in that entire landscape is the point of perfect accuracy, the absolute minimum error. Gradient descent is like giving the network a compass that always points downhill, guiding it to take small, steady steps toward that perfect solution. Which brings us to the big payoff. Why does this specific architecture, deep layers, nonlinearity, backpropagation, why does it matter so much? Because getting this blueprint right didn't just improve AI, it changed everything. I mean, just look at this timeline. For decades after 1969, AI was basically in the dark ages. Then, bam, 2012 happens. A deep neural network called AlexNet completely shatters all the records in a huge image recognition contest, proving this architecture could work on a massive scale. And in that same year, a Google network, after being shown millions of random YouTube videos, taught itself the concept of a cat without any human help. The AI winter was officially over. That architectural breakthrough is the direct ancestor of the tech we use every single day. The Face ID on your phone, those translation apps we talked about, AI that can spot tumors in medical scans, even the large language models that are changing our world, they all stand on the shoulders of this one layered learning blueprint. And that leaves us with one final kind of mind-bending thought to take away. By mimicking the structure of our own brains, we created an incredible tool for understanding the world. But as these networks get deeper and more complex, they start to find patterns and make connections that are completely alien to us, to human thought. The architecture works, we know that, but what it's building on the inside, that might be a new kind of intelligence altogether.